Yeah, going live. Yeah, we're live now. So good afternoon again. We are here. Okay, we have some audio problems. Where is Pierre? See Pierre. Hi. Do you see Pierre, please? Around? No. So I have to take care.
Yes. So you can see. Okay, I don't know how much Lunar is paying.
Sorry for some technical inconvenience. So, okay, we are here now with two exponents of a company called Space Copy, and they are the author or the originators of a novel technology for in situ resource utilization for additive manufacturing for extreme environments on Earth and in space. And in specific, I think we are talking about the moon, right?
Yes.
In view of the Artemis program and the incoming lunar economy and all this kind of thing. So we are Space Renaissance International. We are very much interested in all these topics because, as you know, we are promoting the expansion of the civilization into space and to start absolutely before 2030 civilian space development. That means to move the first steps, industrialization of the geolunar space, of the moon, of the Lagrange points, near Earth asteroids, and all this kind of environments where we can maybe find resources to generate, to produce propellant in space. That will be, in my opinion, the second step after having a reusable, fully reusable launch vehicle. Second step to downsize the cost of any mission in space. So I think what you're doing is very much important from this point of view. So I will not take any time, and I give you the floor for talking us what you are doing. Sorry, because we have two microphones. One is for the environment here, and the other one is for the YouTube.
All right. Fantastic. Thank you so very much. It's a pleasure to be here. So we are here to talk about additive manufacturing in space, additive manufacturing in extreme environments, and most specifically, we're going to center the focus on today's conversation about inhabiting the moon and what it's going to take to get the next generation of spaceflight to the moon on a permanent basis. So to offer a bit of an introduction, Space Copy is an additive manufacturing company based in the United States and Canada. And we're developing out 3D printing systems in order to be able to create infrastructure using local in situ materials. So think products like Lunar regolith and transform that into a feedstock that can then be transformed into sustainable and scalable infrastructure. So things from the habitats to precision tooling fabrication to repair parts and supplies, launch pads, anything that you really think of when you're imagining a lunar settlement that can be created from infrastructure and local materials is what we are capable of 3D printing.
Thank you very much. So, now maybe we could go deeper inside this technology and see something about the tools, the machinery, on whatever you are using. So we have here a presentation, a PDF presentation of your technology, so we can maybe share our desktop and see it. Okay.
Fantastic.
So, okay.
All right. Thank you. Yes, let's get that presentation up on the screen, and I'm happy to get started. One of the unique things too about 3D printing is how diverse its applications are. It has been a heritage technology that's been around for decades and decades. The first time that we talked about 3D printing in space was in 1969 on the cusp of the Apollo 11 mission, and NASA began ideating what it was actually take in order to transform local materials and turn that into a usable infrastructure equipment. And 3D printing and additive manufacturing has always been at the center of the focus. But up until now, there's not really been measurable strides when it comes to being able to commercialize the technology. So upon founding Space Copy, I think one of the core principles for us, and our motto is transforming human exploration methods, was based on that principle of really just trying to understand what the innovation is, what the state of the art is in the industry, and then taking the heritage knowledge that we have from these space agencies that have been researching this technology for so many decades. So behind me here, you can see the presentation that is up on the screen, and it is showing in the live stream. So with that, let me kick things off and give you all a short demonstration of how this technology works. So to kick things off, I'll move to the next slide, please. Let's understand first what is Space Copy. So as I was just explaining, we're developing out these 3D printing systems for space and for Earth. Now, speaking about our terrestrial applications, that would be items ranging from natural disaster areas to combat zones to places where it is logistically challenging or even impossible to get supplies delivered in. So thinking places like Arctic, desert, subsea, as well as other places that you cannot get these supplies shipped in. And in that same note, we bring ourselves to the extraterrestrial benefits. So LEO, any kind of microgravity area like the International Space Station, and of course, the lunar surface. And that's where we're going to be focusing most of the discussion today, is on the lunar surface. Next slide, please. So first of all, let's talk about the challenge that we present ourselves with when we talk about 3D printing in space. And it is really, truly the principle on why Space Copy was founded. So right now, we're looking at the big picture. The cost of Earth to Moon supply transportation per kilogram on a payload is 1.2 million US dollars. Looking at the big picture, if we're talking about Artemis, we're talking about sending 4 astronauts to the surface of the moon. If we're considering a long duration mission of 1 year, that's approximately 22,000 kilograms of supplies that is required in order to sustain these astronauts. Around 70% of that is infrastructure. And that is being created on Earth and being sent up to space. If you tally up what that actual cost number is, you're looking at over $6 billion in just sending up infrastructure supplies out of things that can be created locally. So when you think about that $6 billion figure and that 22,000 kilograms of supplies, take away 70% of that number. And that's the power of what you're going to save with additive manufacturing. And that is the basis of how we created the concept of Space Copy. Next slide, please. All right, so now taking a page and diving deeper into the technical benefits, I want to introduce the 4-stage technology that goes into this additive manufacturing equipment. So I'll break it down simply, and then I'll get deeper and deeper into the technical parts of it. The first stage is what we affectionately refer to as mixing. The more technical term you may be aware of is called beneficiation. That involves the reduction of particulate into a fine powdery feedstock that is suitable for 3D printing. So lunar regolith is comprised of mainly silicon dioxide, depending on where your location is. We're aiming for peak near Shackleton, close to Artemis landing site. So it is a highland simulant. It's around 47% of that silicon dioxide, with around 12% metal and then trace amounts of elements in between, including volatile organic compounds. So we're taking this beneficiation and mixing system, and we are breaking down this particulate from small-sized rocks down to a powder of around 50 microns. And that's being done through the use of a jaw crusher, dual centrifuge mix, mechanical sieve, and lastly, vibrational separation to reduce the amount of electrostatics going into that particulate, and also in conjunction, reducing agglomeration and improving particle roundness. So we move to phase 2, we enter into feedstock sampling. We utilize a Raman spectroscopy laser source in order to be able to obtain the composition and mineralogical information about what this feedstock is created from. So as many of you might be aware, the lunar surface is a very, very dynamic composition from one area to the next and can be drastically different, even 1 meter apart from each other. So that Raman spectroscopy is going in there, is going to scan the top layer of that feedstock and create that mineral profile. That data sent through an algorithm back to the printer, which will automatically update the process parameters. So things like melting point, hatch spacing, anything that you would need to try and improve the density and also the granular uniformity as you're going layer by layer. Third stage, the fun part, additive manufacturing. So the 3D printing itself, we have two systems depending on the complexity and the size and scale of what you're building. We utilize a laser powder bed fusion methodology called selective laser melting for the finer geometries such as precision tooling, fabrication, repair parts. And then for the larger scale infrastructure, printing up to 1 cubic meter in size, we have a fused deposition modeling extrusion printing system with a coupled crucible that's able to create larger scale structures like interlocking bricks, launch pads, berms, trusses, heat shields, you name it, we can do it. Last stage is AI and autonomy. So we utilize each iterative stage of this process through an algorithm and machine learning system. So whether or not you have astronauts on the surface, the interface works remotely as well. So being able to couple all of those systems into one. And last but not least, inside that 3D printing chamber is two special items, I should say. A vacuum chamber, similar to what you would experience in electron beam melting, that creates a pseudo-gravity and near standard ambient temperature and pressure condition to improve the likelihood of the printer's success, as well as an autonomous 5-axis robotic arm that is capable of having multi-tool end effector suites that will have things like grippers, scrapers, saws, whatever you need to post-qualify that equipment. Once it's post-qualified, you're going to run it under that Raman spectroscopy laser one more time. And then you'll be able to understand, is there any kind of cracking or porosity in this part? If it's approved, perfect. That robotic arm is going to drop that part into the collection bin for ready enabled use on the lunar surface. Next slide, please. So after everything that I've just described here, this is a schematic interpretation, and this is the extrusion system for the larger scale infrastructure. It is a modular system, so it ranges in size according to your payload or your mission requirements, or really just what you're trying to build in space. So this is one of the larger systems. We have smaller systems as well. So again, depends on the context of your mission. Next slide, please. So to kick things off with a little bit of where we've been from our founding until now, we were founded in 2022, just celebrated 2 fantastic years, but we have an array of people that helped us get to this point. So starting from left to right, we begin with our partners in academia, a couple of private industry on that side as well. Those are the folks that are helping us right now in our current research and development. As we transition to the right-hand side of the screen, you're seeing some of our clients. So these are folks that we're either in conversation with or have active contracts with. As we transition further to the right, we see contracts. So these are private companies, industry partners throughout North America, Europe, and Asia that have helped get us to the point that we're at right now. And then last but not least, on the far right-hand side, our features. So we've been through various accelerator programs with Techstars, MIT, Singapore Management University, just to name a few. And we've also had a variety of different media features, including NBC News, Business Insider, and also a lot of fantastic press right here at IAC. So it's been absolutely wonderful. Next slide, please. So I've spoken about this already quite a bit, so I will just touch on this quite lightly. The strategic value and, shall I say, unique value proposition behind the technology that we're building is essentially inside that printer. So as I mentioned, has a vacuum chamber, allowing you to create a somewhat simulated gravity environment and simulated standard ambient temperature and pressure to combat the external thermal gradients, solar radiation flares, and electrostatic dust that's being experienced on the lunar surface. That also allows us to swap out the need for shielding gas. So instead of sending up payloads of nitrogen or argon, you're actually able to work with this vacuum system and just 3D print as is. Just closing this up with some of that value proposition comes to sustainability. So I talk about additive manufacturing as a closed loop cycle. And here at Space Copy, the use of localized materials and creating a system that's able to take the raw material and output a fully finished product all in one device is a huge part of our initiative for, again, going back to our logo, transforming human exploration methods. Next slide, please. All right, so as far as current progress goes, we are TRL 3/4, market readiness level 4 as well. We're patent pending, multiple client contracts in place with letters of intent and memorandums of understanding with partners across the globe. And we have a long way to go. We're bidding on contracts actively with various space agencies and government bodies to try and get this technology deployed into terrestrial ecosystems by 2026, as well as in preparation for a cislunar flight opportunity that we have in 2025. Next slide, please. Now, I want to stop and really focus on this slide in particular. This is one of the fun ones. So this is how we got to that TRL-3 milestone achievement. We validated the concept. We worked with various different lunar regolith simulants sourced from various output sources, so off-planet research, space research technologies, Washington Mills, and we took this regolith simulant and we utilized a variety of different methods to down select what type of additive manufacturing works best. So what you're seeing on the right-hand side of your screen, first picture, top right, is a life-size brick measuring 200 by 150 by 80 millimeters, created from the extrusion printing system. And then along the bottom, you're seeing bricks created from a binder jetting, melting, and sintering. So we did find that the melting tended to work best with regards to layer adhesion. Similarly spoken with the extrusion basis modeling. So we did choose those two technologies as our main value proposition. And now we're looking at generating a higher density parts, improving the granular uniformity of the simulants, and also playing around with chemical composition to really understand what we could be doing better to improve geotechnical accuracy in our experiments. Next slide, please. So, performance metrics. We're in the kind of hybrid right now between phase 2 and phase 3 in research and development, also starting to enter partnerships with clients. We've got a bit of a ways to go until the launch date, but things are on an upward trajectory. Next slide, please. So circling back to our operations. So I've talked about extreme environments in Earth and space. This is a page into what our space looks like. We do meet the payload mass and weight requirements, dimensional requirements as well of the NASA Moon to Mars objectives, and our additive manufacturing technology in particular does happen to meet some of the shortfall gaps that were identified by NASA in the planetary decadal survey, as well as in just a general public survey taken by industry with regards to the in situ resource utilization market gap assessment report. Next slide, please. Skipping through this very quickly, we also have the option to adapt this technology for Arctic and extreme cold operations. Obviously, if we're planning on utilizing this technology during the lunar day and night cycle, it makes a lot of sense that being able to deploy this technology into our Arctic systems is a very logical step for proving out those test grounds and really understanding how that technology works. Next slide. Similarly, desert and extreme heat, well, the lunar surface can get up to 390 kelvins. So being able to also have the capabilities to 3D print in the extreme heat environment becomes equally important. So we use solar power to be able to manufacture with. We have a backup generator and battery systems. And right now we are working on understanding what the juxtaposition is between manufacturing with a terrestrial soil or sands in compositional accuracy and dimensional awareness too, to the lunar regolith. So that's something that's currently ongoing, but just to take a page here, we're also looking at that desert and extreme heat operation. Next slide. Now, one of the more interesting ones, because this kind of plays into the microgravity, we have the ability to work underwater as well. So being able to create a system that is working under that reduced gravity environment, working subsea, creating repair parts, repairing legacy equipment, so things that have been discontinued, especially in these austere environments where you really find yourself challenging, especially underwater, to get supplies sent into the place that you need it to be. We're taking the same kind of processes that we are utilizing for space, LEO, cislunar, lunar, and applying it towards those underwater operations. Next slide, please. To close out some of the more important information as to where we've gotten ourselves now, we have won a few awards. We have awards pending from various government agencies. Some highlight pieces that we have here from the Middle East to the United States to Canada to the Ukraine. We have a variety of different grants and awards that we've won. One of the most proud ones for me is the Buzz Aldrin Family Foundation Global Innovation Award that we took home this past spring in California. We were also pleased to take home the Moon Village Association Promo Moon Initiative Award in partnership with the Yuzhnoye State Design Office in Ukraine. So again, absolutely fantastic organizations, further amplifying our global reach in being able to communicate the value proposition of getting this technology to space and also into austere environments and combat zones. Next slide, please. All right, closing this out with a little bit about our team. So we've got a couple of our core members here on the slide. Myself, coming in as CEO and founder with prior experience at NASA with planetary science, heliophysics, and astrophysics. Also as a subcommittee advisor to the United Nations Committee on Peaceful Use of Outer Space, and the chair of the International Lunar Chamber of Commerce, and the region chair of Space Technology and Aviation for the government of Alberta, Canada, where I call home. Also here we've got our lead additive manufacturing engineer, our lead robotics engineer, both from NYU. And here with us today, we also have our senior advisor for extreme environment operations. If you want to say a few words.
Oh, thank you. So everyone, it's a very, very, very great and particular work that until now we are developing. And I'm at the moment fully developed about the subsea operations. And me and my team are developing all the studies with space copy for this type of operation in the next future. So we will be sure that the next year will be a very crucial period for our next steps.
Thanks. So thank you very much indeed for this presentation and for the information you gave us. And yeah, we have a few more minutes before concluding, and I would like to tell you about our initiative, because this boat is not only made by Space Renaissance International, it's our association, but also from our partners, that is the Space 18 SDG Coalition. So we are proposing to add an 18 SDG to the UN 2030 agenda. An 18 SDG based on civilian space development, because space is completely absent from the 17 SDGs as they are. But we consider that space development is the real key factor of sustainability. Without expanding and starting to build in space, the other 17 SDGs are not feasible because of the several crises that are grasping the world will continue to oppress the wars that we have, the horrible wars that we have now ongoing, will oppress the economy and will forbid any further development of our civilization, growth and progress. So we strongly promote civilian space development, and the 18th SDG is exactly with this goal. So we have already 103 organizations in the coalition that are NGOs. We have commercial companies like yours. We have educational institutions like university, the Kepler Space University, just to name one, and the IPSA from France and many others. So we will be very, very enthusiastic if your Space Copy company will join the coalition and work with us for the 18 SDG. What do you think about a fresh look on that? Maybe you heard about it before, maybe not. But may I ask you, what do you think about that?
Absolutely. Thank you so very much. So first of all, we would be thrilled to join that coalition. I know myself personally as a big advocate for STEM and for space, wanting to advocate for greater recognition and really truly just trying to initiate partnerships with consortiums and global organizations to help promote us all getting to space as a global industry. I know that this sector has been very much segmented between regional boundaries. There's things governmentally that have been restricting many countries, many companies from working together in the past. And we at Space Copy believe in really trying to reduce those barriers, to create a space for everyone. So absolutely, that'd be something of
Space for all.
huge interest.
Our-
Space for all.
Space for all, on Earth and beyond.
On Earth and beyond, indeed, for sure. Well, having the opportunity also to do work with the United Nations, I have seen firsthand that we're not quite aligning ourselves with the Sustainable Development Goals that we preach. So being able to close that gap, I know there's things like the Artemis Accords out there, there's the Moon Agreement, there's the Outer Space Treaty, all of these different agreements that consortiums and government agencies have executed upon, but those clauses conflict with each other. There's not a great amount of cohesion between all of these different agreements. And because of this fact, people don't know where to go. Organizations, industry, government, academia. There's such a segmentation between these different industries. And at Space Copy, we're looking to close these barriers as much as possible. So to close out from my side, absolutely yes, be something that we're very, very interested in. Thank you.
Thank you. Thank you very much. And yeah, just to conclude this very interesting conversation, I want to say that a very interesting idea raised up in one of our previous conversation that anyone that will get back to the moon, could it be Artemis or ILRS? We don't know who will be the first, but we will ask them to bring a UN flag on the moon. So really in the name of the whole humanity this time. And we are not equidistant, we are equinear, both to Artemis and ILRS. And we, Space Science International is asking to join both Artemis and ILRS. And we will bring this proposal that they bring to the moon a UN flag. That will be a great thing. Okay. So thank you very much for being with us. And for sure, we will have other opportunities to work and collaborate and make something together. Okay.
Thank you.
Thank you very much. Bye.
Thank you.
Bye-bye.